collection of talks at Real World Crypto. It's been really fun so far. It's great to see everybody. So we have 3 great talks about zero knowledge and forward secrecy, and this will be for the next hour. And the first speaker is Anta Nicolescu from Protocol Labs and the Ethereum Foundation to talk about Snackpack, practical Snark aggregation. Thank you.
Okay, hi everyone. Maybe I can see my slides at some point.
Here they come.
Yeah, great, thanks. So this is a joint work with my colleague Nicolas Gailly from Protocol Labs and Mary Maller from Ethereum Foundation. And it's about how to practically aggregate snarks. So in short, what we are doing here, we are taking a bunch of snarks, many snarks, and we are packing them together into something light and nice and an aggregation proof very small compared to the initial snark. So what are snarks? We already heard in the previous session. They are proof systems that allow to verify NP statements, and they have nice properties such as succinctness, so they are very short in size. They are non-interactive, so they are perfect for decentralized scenarios where the prover just sends a statement and the proof. They are arguments in the cryptographic sense that the adversaries are computational bounded, so a cheating prover doesn't have unbounded power. And they are knowledge soundness, so we have an extractor, and for each prover we can extract a witness for the statement behind. And we can add zero knowledge almost for free. And zero knowledge also reassures us that the proof doesn't reveal any more sensitive information than the correctness of the statement. Okay, so what they are useful for in real world, we use them in decentralized storage systems such as Filecoin. And here we have a bunch of users. Some of them are storage providers, so they onboard storage capacity to the network, so everybody can use this storage to put their data or valuable information there. And they are incentivized by some rewards. So this means that they need to prove that they indeed store the data and they have that storage capacity to the network. So those are the provers. They need to convince us. And other nodes in the network will play the role of the verifiers, which are ensuring that the data is stored, maintained, and secured as claimed by the provers. So this is done in a decentralized way by using a public blockchain where those provers are just onboarding their proofs on the blocks, on the chain, and then the verifiers can freely come and publicly check those proofs. Okay, and in more detail, how Filecoin system works. For each storage capacity we want to prove, we need to split it in sectors of 32 gigabytes and prove them separately. And to prove one sector of 32 gigabytes, we need 10 snarks. So we need to submit all these snarks to the chain. And since blocks are finite, they will get filled by snarks very quickly. And there is also the verification time of these snarks. So before we go to the next block, we need to verify all the snarks in the previous one. So we take some time. And this sets onboarding limit on our system. So this used to be, before Snackpack, 40 petabytes per day. Okay? We were still helping the system to scale by using batching for the verification. So I said, one block full of snarks should be verified before the next block will come on. So we can do this by batching multiple snarks together in the verification process, and this means that we earn some time in terms of the verification. But a better way to scale this system is to use aggregation. So this is what we will design in Snackpack. Aggregation not only helps in faster verification, but also saves us in proof size. So the verification time and proof size are small. Okay, so what do we need to know as background before understanding the techniques we are using in Snackpack? Some basic stuff about bilinear groups. So here we will consider two groups, G1 and G2, the source group, generated by G and H. This is a multiplicative notation, which I prefer for this talk. And E is a bilinear map, or a pairing, that takes two elements from the source groups, G1 and G2, and gives an element in the target group. And has this very nice special property that all the exponents are multiplied in the target group. Okay? So having this in mind, we will talk about Groth 16, which is the state-of-the-art Snark that we will aggregate with Snackpack. So we start with Groth 16 Snark proofs that have these three algorithms. The setup, which generates a trusted setup, which has some group elements there, some very structured trusted setup. We will call it CRS. Okay, then the proof consists in three group elements. A and C are group elements from the first group G1, and B is an element from the group G2. It's good to keep it in mind, but I will repeat it in this talk. And the verification, I'm simplifying things here. I know Jens is in the audience, so I don't want to. Okay, so this is a pairing check equation that is needed for the verification, and consider that A, B, C come from the proof, and D is just a combination of all the inputs, like all the statements for the proof, and some verification key. So this is one check that the verifier has to do in order to see if the proof is correct. So what happens when we have many Snarks? So we have this bunch of proofs here with a lot of A, B, C elements, and we want to verify it using some D, which is the one that the verifier can compute by itself. So many pairing checks will be done by the verification. And instead of doing this, as I said, there are batching techniques that makes the verification simple and faster. So if we take all these pairing checks and we just sample a randomness and we compute a linear random combination of them, then because everything is bilinear and nice, the properties are preserved, and we can, at the end, obtain a single equation. So remember, multiplicative notation means that the multiplication by a randomness R goes into exponent. So this is a single equation, randomized, that checks at once all the left equations here. So this is what the verifier will do for batching. And rewriting this equation in a different way will lead to this equation here in the left. And what we'll do for aggregation. So the idea is really simple. When instead of sending all these AI, BI, CIs to the verifier, the prover itself will do this recombination with a randomness. So this linear random combination will be done on the side of the prover. So the verifier doesn't have to deal with such computation, never has to read all the proofs. So we will compute this value, ZAB, which corresponds to the left part of the equation to be checked, and ZC, which corresponds to the prover's contribution to the right part we need to check here. Okay. Great, sounds good, but we will need just to receive these elements from the prover and then check it as a verifier, but who will trust that those are correct, right? So the prover can introduce a cheating strategy, rechange some of the proofs and affect the soundness if it just sends these two values. So we need to send these two values, but also a proof that they are correctly computed with respect to the initial proofs, AI, BIs, and CIs. Okay. So let's go to the actual construction and how the prover will convince us of this. And our tools are coming from a previous result by Bunz et al., which are proofs of inner pairing products and their application. And those inner pairing products are generalizations of pairing products, inner products, for group elements. So vectors come with elements from a group, from G1 or G2, and they are come in two flavors, MIPP is the one in yellow there. Like, we can compute multi-exponentiations of a committed vector from the first group. This is the vector A from the first group, with exponents in the field. Okay, BIs are exponents. And the second type is TIPP, which computes these pairing products between two vectors of group elements. A is in the first, A comes from the first group, and B from the second one. So those are the tools we have. We know how to prove these two relations for any vector A and B committed in some form. Okay? And now if we stare a little bit of what we needed to convince the verifier in our aggregation idea, we have the ZC and ZAB that should be exactly coming from some proof elements AI, BI, and CI. Okay? If we rewrite it with the notation we have from MIPP and TIPP here, like inner pairing products, we see that ZC is just an inner pairing product, a multi-exponentiation of C with some random vector R. And ZAB is the pairing product from the vector A, which comes from the first group, and B to some randomness, which is a vector in the second group. So it's great. We can use this just to convince the verifier that these two values are what they are supposed to be. So what we have to do is to commit to A, B, and C, the vectors from the proofs we want to aggregate, and then compute the values ZC and ZAB and use MIPP and TIPP to prove that those commitments and the values correspond to what is expected. The problem here is that we want to deploy this system as soon as we can in the real world, so in our decentralized storage to fix the scalability problem. And committing to these vectors needs some public key, which is a very structured, there are structured parameters that need to be trusted. So this in real world requires a complicated ceremony between multiple participants that are independent, and they have to run MPC protocol together in such a way that after they run the protocol, they commit to destroy their machine and all the randomness and the secrets they have there. So it's not something we want to repeat like often in practice. And the idea behind our aggregation is to just use trusted setup from the GROT16 system that we aggregate. Because GROT16, as you saw, has also some trusted setup. So let's reuse parts of that trusted setup in order to construct an aggregation scheme on top of it. And the trusted setup, the exact part of the trusted setup from GROT16 we need are these powers of tau, which are like powers of a secret element tau computed in the first group, in the exponent, and in the second group in the exponent. Okay? And we have such ceremonies already well established and well recognized that generated trusted setup for this. And we will need 2 copies of such a trusted setup that are compatible in the sense that they have the same generator G and the same generator H for the 2 groups of elliptic curves. And we have such 2 compatible trusted setup that are well established, and one is from Filecoin and one is from Zcash. And we will use this in order to construct our aggregation scheme. So what we need to do is to construct new commitments with this trusted setup elements as commitment keys. So one commitment here for us to commit to a group to a vector of group elements in the first group, we need to use the vectors from the trusted setup in the second group with the respective random powers alpha and beta. And the commitment will be 2 target group elements for committing to one long vector in one group. And the nice thing about it is that if we can combine a vector from the first group and a vector from the second group, we can commit together to both of them with the same cost, with 2 target group elements. So we put together in two target group elements, these commitments to the vector A and to the vector B in the first and the second. Okay? And now the Snark aggregation. Once we have these commitments, we can reinstantiate a version of MIPP and TIPP and do the Snackpack final scheme that consists in taking the vectors of the proofs we need to aggregate, put them into these commitments. So we commit to A and B together and to C separately. So we have 4 target group elements. And then we run MIPP and TIPP over this. And this is a log n long proof that demonstrates that those commitments and these values here are computed as expected. Okay, so ZC and ZAB are the values we need to give to the verifier as a batch verification terms. And what's done by the verifier here is just taking log n commitments from this MIPP and TIPP, and those are target group elements, and check the MIPP and TIPP relation using that proof, and then check the final relation between remember those ZC and ZAB come from the linear random combination of the initial terms, or initial group elements from the proof. Okay, and if this equation holds, then all the proofs together hold. Great. So we implemented this. It's real. It exists. It's implemented in Rust, open source, available on these links. So we use the BLS12 course and the library dedicated to this. The CRS is a recombination LSA of Filecoin and Zcash, and the benchmarks are performed on these machines. Okay, so some numbers here. For the verification, we compare with the batch verification we had before. So it starts to pay off after 32 proofs. So that's pretty nice. And it also is a lot more efficient than the batch verification, which is in red here. Also relies on parallelism. We have a lot of optimization for these MIPP and TIPP protocols together. We do a lot of batching also for the pairing checks and other curve operations. Okay? And for the proof size, of course, that was the initial challenge to reduce the proof size, so it's logarithmic in the number of the proofs. Compared with the linear growth of the proofs without any aggregation. It's based also, because these are target group elements, it's based on some compression techniques that makes them lightweight. Also, this is inspired by Relic library. Okay, and for the aggregation time, this is the overhead the prover has to pay in order to compute the aggregation, so to apply Snackpack to the already existing proofs. And that's not too bad. Like, we see that it's reasonable till 2 to the 10, and then becomes like minutes, terms of minutes. But it saves so much time and so much verification time that it's worth paying this price. Okay, so let's go back to our application and see how it helped. So nowadays, we have 1,000 more proofs on the chain due to this Snackpack optimization. So each sector, as I said, was consisting of 10 snarks. So we take many sectors provings, and we put it together in a snark. So we have light proofs, so the blocks are not getting full so fast. Also, the verification time is 20 milliseconds for 2,000 snarks. So that's way faster than we had before. In practice, we get 200 more sectors than before. Okay, so what I presented, our main motivation was to make this practical as soon as possible, and what was the most difficult was to get rid of a new trusted setup that we need to run. But it's still not transparent. It still relies on trusted setup. So next steps will be to explore other ways to aggregate snarks, maybe in a transparent manner. We have nice optimization. We continue to optimize this system, so there will be a follow-up work. And we were focusing only on Groth 16 construction, but this generically works for any pairing check equation. So we were wondering, are there other applications in practice that consist only in pairing check equation, and a lot of them that need aggregation? And that would be a nice extension for our work. Okay, that's all I have. Thank you.
All right, thanks. Any questions? We're right on time. Anybody coming to the line? And it seems like there's nothing on Zulip either, so thank you so much. Anka.
Thanks.
Our next speaker is Paul Grubbs, who's going to talk about zero-knowledge middle boxes. Please welcome Paul.
Thanks, everybody. This talk is going to be about resolving fundamental tensions between privacy and policy enforcement in networks. We all know that encryption is becoming ubiquitous. Protocols like TLS 1.3, where a client and a server use a handshake to establish a shared secret and then use it to encrypt their traffic, improve privacy by hiding the contents of network traffic. Increasingly, protocols like encrypted DNS are hiding more and more of the metadata of network traffic as well. This makes the basic task of enforcing policies in a network much more difficult. Today, networks rely on middle boxes to enforce policies by scanning traffic. And a middle box is, you can think of it as just kind of a router that can perform some general purpose computation on the traffic. And so if the middle box detects that the traffic is compliant, it lets the traffic through. Otherwise, if it detects a sort of violation of the policy, it blocks the traffic. Middle boxes enforce dozens of different kinds of policies in networks, everything from like DNS filtering to data loss prevention and many, many more. So the motivating question of this work is really, is it possible to resolve this tension and have both privacy and policy enforcement? This question itself is a little bit polarizing. I think many network administrators would argue that in networks where you need to enforce policy, you just simply shouldn't have encryption, whereas many cryptographers and people in this room might argue that networks should really only enforce policies that don't require access to plain text data. And so if we want to find a solution that accommodates both of these positions, we can articulate just a few basic requirements. The first is that we shouldn't have to weaken encryption. We should have the same kind of privacy guarantees as regular encryption, except possibly to reveal to the network that the traffic is policy compliant. So that's kind of the only thing we should reveal. Second, networks should still be able to enforce policies as they did before. So a corollary of this is that clients shouldn't be able to unilaterally bypass the middle box and sort of send non-compliant traffic. And finally, we shouldn't have to change the server, but we might change the clients in the middle boxes. This is a requirement because there's a lot of good evidence that clients are a lot easier and faster to update than servers. For example, in January of this year, only 51% of TLS servers supported TLS 1.3, which is 4 years old now, whereas 50% of Chrome users were already using a browser version that was only a month old at the time. So it seems like clients are easier to update. Another corollary of this that kind of no changes thing is we don't want to introduce additional trust assumptions into the system, so like no new root CAs and no trusted hardware. So there has been some prior work on this subject, but all of it violates at least one of these requirements. So like multi-context TLS and blind box require weakening encryption and also server changes, and SGX-based solutions require new trusted hardware. There's one very important non-requirement that we should articulate, which is that we don't want to prevent circumvention by knowledgeable users. So what we would want to do is really maintain the status quo that exists today, where middle boxes can sort of enforce a safe default between privacy and policy compliance, but advanced users can sort of still get around the middle box if they choose. So what we definitely don't want to do is build infrastructure that can't be circumvented and sort of be misused for censorship. So in short, what we want is some sort of way for the client to convince the middle box that their traffic is policy compliant without revealing anything else about it. And so it turns out that there's a cryptographic primitive that can really help us here, and because this is the zero knowledge session, you can probably guess what it is. This is zero knowledge proofs. So if you're not familiar, that's okay. I'll just quickly give a basic explanation. So a zero knowledge proof is a cryptographic protocol between a prover and a verifier, and it allows the prover to convince the verifier of the truth of some public statement with two security requirements that we care about. The first is that the prover shouldn't reveal sort of why the statement is true to the verifier. It should just convince it that it is true. This is the zero knowledge property. And the second property is that the prover can only convince the verifier if the statement is true. So this is the soundness property of the zero knowledge proof system. So zero knowledge proof, we can think of it for this talk as just being a single message from the prover to the verifier. So the prover runs some protocol to generate a message and send it to the verifier, and the verifier checks the message using some verification procedure. So we're going to use zero knowledge proofs to build a new kind of middle box abstraction. We call it zero knowledge middle box. That's going to work as follows. So when a client joins the network, it's going to get a description of the network's split kind of policies that they want to enforce. The client and the server will use standard encryption protocols to establish keys and communicate and encrypt their traffic. But the client will, in addition to sending its encrypted traffic to the middle box, it will additionally include a zero knowledge proof, roughly of the public statement that, this ciphertext contains policy compliant traffic. And the middle box will verify this proof, and in so doing gain an assurance that the traffic is compliant, and if the proof doesn't verify, then it'll just block the traffic. So let's just review our requirements again and check to make sure that our requirements are met. So we can conclude that we didn't weaken encryption because we're sort of using standard encryption, and as well the zero knowledge property of the zero knowledge proof system hides the traffic except for the fact that it's policy compliant. So the middle box can still enforce policies because the soundness property of the zero knowledge proof system prevents the client from lying about traffic if it's not policy compliant. And finally, we didn't have any server changes because the middle box strips the proofs out if the traffic is compliant and doesn't forward them to the server, so the server doesn't really even know about this interaction. So when we first came up with this basic architecture, we weren't even really sure it would work. And the reason why is because zero knowledge proof projects that have kind of that are looking to deploy zero knowledge proofs in practice efficiently really heavily rely on kind of tailoring the computation proved in zero knowledge to be amenable to being proven with the underlying machinery of the zero knowledge proof system. Kind of like Howard's nice talk earlier today really went into detail about how they do this. Unfortunately, because we want to maintain sort of compatibility with these legacy protocols, we just have to sort of take them as they exist today. So like protocols like TLS 1.3, this is the key schedule of TLS 1.3, this like very, very complicated diagram here. So we sort of have to figure out how to adapt the zero knowledge proof machinery to be efficient for very complex protocols that weren't designed for zero knowledge proofs. And so what we found, much to our surprise, is that not only does this basic architecture work, but that zero knowledge proofs about properties of TLS 1.3 traffic are already close to practical today, which is a very, very exciting outcome of this research. So in the remainder of this talk, I'm going to tell you three things about zero knowledge middle boxes. I'm going to go into a little bit more detail about the kind of circuit model of the proofs, and then I'm going to explain a core technical problem that we had to solve, which is building efficient decryption circuits for TLS 1.3. And then I'm going to explain an application of the zero knowledge middle box framework to building filtering for encrypted DNS. And then finally, I'll speak very briefly about some future work. So before we talk about specific computations, I just want to fill in a little bit of detail about the kind of machinery of the zero knowledge proof. So zero knowledge proof, for our purposes, proves the satisfiability of some arithmetic circuit, and how this works isn't so important. But what we need to know is that the arithmetic circuit has public inputs and private witnesses. And in a zero knowledge proof protocol, the prover will run some prove algorithm that generates a proof, and conceptually it takes as input the circuit that's being proven and the inputs and the witnesses. And additionally also some zero knowledge proof systems have a trusted, as Anka just said, they have a trusted pre-processing step that sort of generates a statement-specific proving key, which we'll sort of abstract away in the talk. So the prover generates this proof and then sends it to the verifier, and the prover, the verifier runs this verify algorithm that takes as input the circuit and the input and the proof, and then outputs a 0 or a 1. And if the verify outputs 1, the verifier gains an assurance that the prover knows some witnesses that cause the circuit to output 1. But zero knowledge sort of hides what those witnesses are from the verifier. So basically with this, building a zero knowledge middle box kind of boils down to constructing a circuit that roughly proves that when you decrypt the traffic and run some sort of compliance check on the underlying plaintext, you get a 1 as output. So we can think of the input as being the ciphertext that the client is sending, and the witness being the key that it's using to encrypt its traffic. And so we need to build this kind of a circuit, but because these circuits are very complex and they're also like protocol specific in multiple ways and also sort of policy specific. In the paper we give a sort of like 3-step pipeline for building these zero knowledge proofs to make it a little more modular. So we have this channel opening step that just decrypts the message, decrypts the ciphertext and outputs the message, and then parse and extract sort of extracts the policy relevant data from the underlying plaintext and sort of deals with the network protocol part of the proof. And then finally the policy check verifies that the data is compliant. So I just want to zoom in a little bit on a specific step which is interesting and challenging. So it's building this channel opening circuit for TLS 1.3. So this is the circuit that decrypts the ciphertext. So the question is, how do we decrypt a TLS 1.3 ciphertext? And so a first attempt is to just express the TLS 1.3 like record layer decryption in an arithmetic circuit, which under the hood is running some decryption for some kind of like AAD, like GCM or maybe Cha-Cha-20 Poly 1305, and then output the plaintext if the AAD decryption succeeds, and then if it fails, we sort of short circuit the rest of the computation, then go and output a 0, so like false. Unfortunately, and interestingly, this doesn't work at all. There's a severe problem with this approach, and the problem is that TLS 1.3, the record layer decryption isn't binding in the sense of a cryptographic commitment. And so what this means is that it's possible to craft ciphertext that can have multiple different decryptions under different decryption keys. And so the reason why this is a problem is because the prover, the client, can essentially lie about what it's sending to the middle box and construct a ciphertext that has one decryption for the server and one other decryption for the middle box in a sense like in the proof. So kind of lie about what it's sending in the proof. So fixing this was challenging, but the basic idea of how we're going to be able to fix this is to add an additional constraint to the channel opening circuit. And what the constraint is going to force the client to prove is that the key that it's inputting to this arithmetic circuit was actually output from the handshake that it performed with the server to set up the key. So we're going to have the client give as input, in addition to its ciphertext, the transcript of the handshake that the middle box saw when it established this secure session, and then add this kind of key consistency check to the proof. And then if the key consistency check fails, then that's what will let us short circuit the computation and go to the end. But otherwise, if it succeeds, then we just sort of do the TLS decryption and then output the message. So then the question really boils down to how do we build this key consistency check efficiently? And because I only have 20 minutes and not 2 hours, I'm going to give you the short version. So there's a simple way to build this key consistency check, which is basically taking the TLS 1.3 key schedule that I showed earlier and expressing it all in an arithmetic circuit and then proving the whole thing from the input of the handshake and then basically proving that the key is equal to the one that you get out of this key derivation. Now this works. In the paper we prove that like it's not so hard to see because like the Diffie-Hellman values in the handshake are like binding commitments to the shared secret. Like this prevents the client from lying about the key that it puts into the proof. But this is like really hideously slow, and I'll show a number later in the talk, but it takes way too long to do this in the arithmetic circuit. So what we observe in the paper that lets us kind of get rid of this inefficiency is that the TLS 1.3 handshake is sort of special in a sense that it has a message in the handshake. If you're familiar with it, it's the server finished value. It has this message that sort of commits to the intermediate steps of the key schedule of TLS 1.3. And so what we do is sort of repurpose this message to check the correctness of these intermediate values that the client inputs to the proof, and in so doing sort of cut all of the expensive part of the key derivation out. So we get rid of the like the Diffie-Hellman stuff and the hashing the transcript and that kind of thing. But there's a lot I'm not saying about this, so please see the paper. And so one thing about this key consistency check, which is really interesting that I want to highlight, is that this key consistency check, because TLS 1.3 keys are usually established once for an entire session, the key consistency check can actually be amortized across all the proofs that the client sends about in a session. So what the client can do is at the beginning of a session, before it sends any traffic, is sort of send the middle box a hash along with the proof. And the proof says that the pre-image of this hash is consistent with the handshake that I just performed to set up this channel. And then the middle box can store the hash, and then later, when the client wants to do a channel opening, rather than redoing the key consistency check, it can just sort of give the hash that the middle box already knows as input and say, hey, middle box, the key that I'm doing is consistent with this proof that you already checked about the key consistency. So this can get rid of the key consistency check in the per packet proofs entirely. So just pop up for a second. I just told you some technical stuff about the way we build circuits for zero-knowledge middle boxes. But I now want to explain how we actually apply the zero-knowledge middle box framework to real applications. So I'll talk about filtering encrypted DNS. So if you're not familiar with DNS, that's all right. DNS is basically just a phone book for the internet. It translates human-readable domain names to IP addresses. And DNS queries reveal sort of the full list of domains that you visited while you're browsing the web, so they have huge privacy implications. So for example, if you're visiting a political party's website, you might reveal something about your political affiliations from your DNS queries. And because of this, a lot of people are thinking really hard about ways to make DNS more private and deploying encrypted DNS protocols like DNS over HTTPS and DNS over TLS to improve the privacy of DNS traffic by encrypting it with a shared key to the DNS recursive resolver that the client contacts. And crucially, this DNS recursive resolver is often not the one that the network might want the client to use. It might be a remote resolver like from Cloudflare or Google. And this encrypted DNS, in the last couple of years, has become the default mode for DNS in major browsers like Firefox and Chrome and Edge. But because the encrypted DNS by design hides the DNS queries from the network, it creates a huge tension between policy enforcement of DNS filtering and DNS encryption. So this tension is especially acute in networks where filtering is legally required. So for example, in the United States, a law exists called the Children's Internet Protection Law, which was passed in 2000, that requires the administrators of certain educational and library networks to filter internet access to prevent children from seeing obscene content. And so when Firefox was deploying encrypted DNS, in part because of the pressure from these groups who needed to filter using DNS, they built a sort of kill switch for the network into their browser. So Firefox, when it opens up, sort of asks the local network if it's allowed to do encrypted DNS, and if the local network says no, then Firefox will disable encrypted DNS and just do plain text DNS. And so I think this is a really remarkable thing that I just want to dwell on. So Firefox, I would say most people would agree, is a pretty privacy-focused browser. And exactly because of this tension between privacy and policy enforcement, they were forced to build sort of a downgrade attack into Firefox to prevent the use of privacy-enhancing technologies, which is an interesting and I think interesting motivational outcome for this work. So to solve problems like this, I'm going to show just briefly how to build a zero-knowledge middle box for filtering encrypted DNS. So the first thing is that the network is going to take its block list and build a circuit, as I described before, with the following 3 steps. So channel opening is going to be the thing I described before for TLS 1.3. Parse and extract is going to check the format of the DNS query in the plain text, and then extract and deserialize the domain name from the DNS query's wire format to like a human-readable format. And then policy check is going to verify that domain name is not a member of the set of all the blocked domains. And the way we're going to do this, I won't go into detail, but this is like a really standard technique using like a sorted, like verifying paths in a sorted Merkle tree. So the clients get this circuit and the block list when they join the network. And then they use standard TLS 1.3 to establish a shared key with the remote resolver. And then when they want to make a DNS query, they include a sort of proof of that this arithmetic circuit is satisfied. And they include witnesses for the policy check portion of this that proves that their domain name is not in the block list. So I'll defer most of the details to the paper, but I do want to say just two things. The first is that for DOT and DOH, this basic circuit template works with very few modifications. The only thing that really needs to change is the parse and extract step, so how the plain text is processed to extract the domain name from the DNS query. And the second thing is that we're sort of assuming that the block list is public and can be given to every client here. In the paper, we show that if you don't want to give the block list to the client, there are ways to hide this if you can incur additional computational cost for the proof and an additional round of communication. So if you want, you could think of this as being some sort of private set intersection-like protocol, roughly, but see the paper for more details. So we implemented this zero-knowledge middle box for encrypted DNS, and I'll just briefly go over some results. So we used the XJ Snark zero-knowledge proof front end to build arithmetic circuits out of our zero-knowledge proof, sort of like in a high-level language, and we compiled them to an arithmetic circuit. And then we used the Groth16 zero-knowledge proof backend with 8 threads for the prover. And so what we found is that first we did a benchmark, like a micro benchmark, this key consistency check, and found that the baseline that I described is indeed like very inefficient. It has like 7.5 million gates in this circuit, so it's quite a large circuit, and proving takes about 94 seconds for a key consistency check. It additionally requires the client to store about a 1.2 gigabyte proving key when it joins the network. But because the Groth16 proofs are quite small and have constant verification time, the proof size and the verification time here are like constant, 128 and 5 milliseconds. What we found is that this optimized circuit that we came up with actually improves things quite a bit here. It reduces the size of the circuit by 7x and the proving time by 6x. So it produces a really important improvement, although arguably this isn't yet close to practical, but this is still a pretty big improvement. So we also benchmarked our DNS case studies. So excluding the cost of the one-time key like session setup above, we found that for DOH, it takes about 6.8 seconds to generate a proof for a 500 byte ciphertext, and for the AES cipher suite in TLS. But for DOT, the costs are much less. So for DOT and Cha-Cha in TLS, we found that we can generate a proof for this DOT filtering functionality in about 3 seconds, which is not practical by any means yet, because waiting 3 seconds to do a DNS query is a little bit prohibitive. But this number, I think, for a first implementation of this kind of whole framework, I think this is a very, very exciting number, and there's a lot of tools in our toolbox to get this cost down. So briefly, with the last like I don't know how many minutes, I'm just going to talk about some ongoing and future work that we plan to do. So we took our kind of arithmetic circuits, and we ported them over to a newer zero-knowledge proof system called Spartan. And Spartan is interesting because it has a different trade-off between prover time and proof size and verifier time. So what we found that just by porting to Spartan, the cost, the prover's time cost of setting up a TLS session goes down to just 1.7 seconds, which is a huge, like a 10x improvement over the previous implementation. And now the proof size and the verifier time are a little bit higher here. But personally, I think that because this is a one-time setup cost, and because 49 kilobytes really is pretty small in absolute terms, I think these costs are still like on the verge of practical. Feel free to disagree with me if you don't believe that. And we also haven't yet finished implementing all of our DOT case study in Spartan, but what we found is just the decryption part of the DOT circuit, which is like about half the cost, a little less than half the cost overall. Doing that takes only like 0.2 of a second for the decryption, which is a really, really remarkable thing. So you can imagine that these costs would like maybe roughly double for the full circuit. So it's like, think like something like 0.4 of a second for just the prover time, and then the overall end-to-end latency increase of this DOT could be as low as like half a second. And again, here the proofs are larger. We have some ideas to get this down. So maybe this isn't like quite practical in terms of the bandwidth overhead yet, but I think these are really, really exciting initial results for this ongoing work. So just in conclusion, my co-authors and I initiated a new line of work on zero-knowledge middle boxes, which use zero-knowledge proofs to resolve tensions between privacy and policy enforcement in networks. I showed you an application of zero-knowledge middle boxes to DNS filtering for encrypted DNS. We designed zero-knowledge middle boxes for DOT and DOH, and in the paper we also described two other case studies. One is doing resolve or allow listing for oblivious DOH, which is sort of like a version of DOH that has additional client privacy, so it uses kind of a one-hop proxy architecture. And the other thing that we showed is allowing clients to prove that the underlying traffic of their TLS session is HTTP. And we are really, really excited about zero-knowledge middle boxes. We think that this zero-knowledge middle box framework has a ton of potential to solve really, really challenging problems that exist today in networks, and also just in terms of research, raise like really fascinating open problems in like systems and networking and cryptography. So with that, I'll take any questions, and thank you very much for listening.
We're over time, so maybe one very quick question.
Sorry about that.
Can you combine, on your penultimate slide, can you combine Spartan for the, it's set up with Groth 16 for the actual messages? Can you combine the two?
In principle, yes, but I think the concrete prover time might be too high. But that's an interesting, like doing some kind of recursion is an interesting idea, yeah. Okay. Thanks, everybody.
Thanks, Paul. All right, so our final speaker is Christoph Streix, who's going to be speaking about puncturable encryption. Please welcome the speaker.
Yep. Thanks, Nick. And from zero knowledge to forward secrecy, or forward security, as I will call it in the talk. Forward security is omnipresent nowadays, right? So every day we use it, browsing the web, and also messaging via Signal and so on. But actually, when you want to deploy it in a non-interactive setting, it gets kind of hard. And currently, there's only one larger player. I will not reveal it now, but later, who is doing this. And punctual encryption here comes in. So this non-interactive setting, it's much harder to achieve, and that's where we depart. So my name is Christoph Streix. I'm from AIT Austrian Institute of Technology in Vienna, and this joint work with Sebastian Ramacher and Daniel Slamanik. So the cryptographic community has developed beautiful tools, ranging from signatures, key exchange, secure communication, secure computation on data, and so on. But even if built correctly, all security guarantees rest at least on the security and trust of the cryptographic keys, right? So and in the following, I will show you a few slides as applications where the security and trust, where they are exploited. So most prominently in 2014, the Heartbleed bug enabled to extract keys, usernames, credentials from servers using an unpatched version of OpenSSL. So those keys could have been used to impersonate users or to spy on communication. There is so much in the cryptographic literature on the topic of key extraction, and just at this symposium here yesterday, two beautiful works were shown and presented. The left one is on the OpenPGP standard and the encryption algorithm Al-Kamal to extract keys there in a cross-configuration attack, and the right one exploits recent Samsung phones and their Android hardware-backed devices to extract keys. But also we have the human factor, right? So usually to communicate with security teams, you publish or you put out public keys, right? On the left, you see an example where an Adobe security team puts the public key and the private key out. And even though the secret key was encrypted with a passphrase, you should never publish the private key, right? On the right, this is an example where an Amazon engineer leaked a gigabyte of sensitive data to GitHub. And the interesting point here is that this was discovered within minutes. Yeah, so, and as it turns out, leaking things or private keys or something like that on GitHub is a thing. And I researched this project called Git Guardian, yeah, was researching the topic, and yeah, you have to think that when you're publishing something on GitHub, it will be there forever, as it is a version control system. So, additionally to security and trust of keys, we should also think of increasing the resilience of cryptographic keys as key leakages happen. And particularly in key establishment, this can be a severe issue, right? If a secret key leaks, all data is immediately in danger, ever encrypted, ever sent over the wire. One mitigation strategy is to use forward security indeed, as this keeps old data safe. And this is efficient, as said in an interactive key exchange protocol and mandatory in modes, which we have seen in TLS 1.3, resulting in over 99% of internet sites surveyed by Qualys SSL labs, at least supporting one or at least some form of forward security. Furthermore, this is highly recognized by industry, by the larger players, Google, Apple, Meta, Microsoft, and Cloudflare. But as I said in the beginning, in the interactive setting, we are fine, but in a modern, maybe more interactive setting, this is much harder to achieve. And here comes non-interactive forward security. So what is this? The basic two requirements we have in the non-interactive setting is that we have a long-term fixed public key. So I will focus on encryption in this talk, and minimum to no state between entities. This is particularly the case in distributed setting with many decentralized identities, and here comes the larger player. Dfinity recently deployed the non-interactive forward security in their non-interactive distributed key generation and key resharing protocol, which is quite nice. But how to even achieve this? So what you see here is an example of non-interactive forward security. You see a client on the left and the server on the right, where the client has the public key of the server. Now it's important to note that this is epoch-based, meaning that the client and the server both, they maintain, let's say, a coupled clock, something for epochs, where epochs can be from 1, 2, 3, 4, and so on. And the client now wants to encrypt a message using the public key and attaching the epoch, for example, here 1. The server now can use its secret key, SK1, to decrypt the message. And after the epoch is over, the server can evolve the secret key to the second epoch, meaning or guaranteeing that all ciphertext encrypted under epoch 1 are not decryptable anymore, right? So this is reminiscent of Canetti-Levi-Katz from 2003, and it's important to note here that we want to have compact parameter sizes, and indeed it makes the construction highly non-trivial, where the parameters must be independent of the number of epochs. So, but what is the problem here? So actually we have kind of two problems. The first one is, okay, we have to agree on some epoch, how to sync this. And the other problem, much larger, is that within epochs, we do not have forward security guarantees of ciphertext, right? So as it turns out, when you want to do it in practice, you require loose synchronization. So this epoch should not be seconds or minutes, but should be maybe days or something like this, because it's required for practicality. Then the problem is that this epoch, this window, is quite open. So leaving all the data which is sent in this epoch vulnerable. So the solution is here. It was published in 2015 at Oakland from Green and Myers, and it's called punctual encryption. With this primitive, you can now fine granularity achieve forward security for all data non-interactively. So what is punctual encryption? Compared to the slide we've seen before, compared to the epoch-based approach, we have now taken a tag-based approach. Essentially, that you now attach a tag to a ciphertext. And you have, when you have a large number of tags available, you can attach enough text to ciphertext, let's say 1, which is uniquely defined as ciphertext, and the server now can uniquely evolve the secret key, particularly on that ciphertext. For example, here there's ciphertext for PK under tag 1, and the server can, after this decryption, it can evolve its secret key to a secret key SKT1, excluding particularly that ciphertext. So this is a much more fine-grained approach. And it's actually a common encryption scheme we've seen, plus an additional puncture algorithm. So the keygen outputs a public key, the long-term fixed public key, and the initial secret key, SK epsilon, and encryption takes now a tag and a message and outputs the ciphertext associated to a tag T1. Puncturing upon decryption now can particularly modify a secret key such that the guarantees are that this ciphertext associated to the tag T1 cannot be decrypted anymore. Moreover, there's a distinguishing feature here in punctual encryption that you can do it repeatedly, which essentially means that you can add more text to secret keys and exclude more ciphertext from being decryptable. So what has been done in the cryptographic literature after the initial introduction in 2015 for asynchronous messaging? You see over the timeline, you see the actually application areas, where these are ranging from zero RTT key exchange to works on searchable encryption, cloud backup, Tor, content delivery networks, and so on. And below the timeline, you see the actual works appearing. It's interesting here that there is we have a crypto community, papers published at Eurocrypt and AsiaCrypt, for example, and also security community, papers published at CCS or NDSS. Particularly, I want to mention here the work on searchable encryption, where they have several papers in CCS and NDSS, where punctual encryption is a useful tool. And also a work from OSDI on mobile cloud backup, which uses punctual encryption. So given those examples, in the following, I want to focus on two more. And these are zero RTT key exchange with forward security and replay protection, and forward security for content delivery networks. So for the first application, the goal is to send cryptographically protected data non-interactively, meaning in zero RTT or zero round-trip time, just want immediately send the data, but want to have the guarantee that they are forward secure and replay protected. The incentive here is you want to reduce communication costs. The problem is that conventional key establishing modes like TLS, for example, need at least one round trip to achieve the forward security. So let's have a look at TLS, how this works. So we have a client on the left, server on the right, and the client starts with sending a client hello. The server responds with the server hello and sending some additional data. And only then the client can send the payload and it achieves forward security. So is this necessary? Actually, there is a zero RTT mode in TLS, which is called early data, and where this client and the server have a pre-shared key, PSK, and then the client can send with the PSK can send the early data encrypted. The problem here is that we do not have forward security guarantees with the early data. So when using puncture encryption, and there have been several works, they're using a time-based version of that, where we have only a loose synchronization, which is okay. The client can now take the public key of the server and tag it, and then send the ciphertext over to the server. This achieves forward security and replay protection in zero RTT, and it was done first by Günther et al. In 2017, and later the most efficient version currently available is the Bloom filter encryption scheme. And there have been some evaluation in the last years at Cannes 2020, where they looked at how to implement that in Quick. So how is using punctual encryption or using Bloom filter encryption particularly, how is it measured compared to the Google Quick protocol? And this is quite fairly okay. So if you want to integrate forward security and replay protection using the Bloom filter approach to achieve zero RTT with forward security and replay protection, this could be an option. But still, I have to mention here and be honest that research is needed for efficiency. Okay. So furthermore, my colleague Sebastian Ramacher integrated this in OpenSSL. So just go to his GitHub account and try it. And also, he just recently implemented it on the Raspberry Pi. So we also try to do it in that domain. And yeah, basically, this sums up this use case. So the second application is for forward secure content distribution networks. And content distribution networks, or short CDNs, what is the goal? The goal is to get the TLS secret keys closer to the customer to achieve low latency. And there's actually a nice solution by Cloudware out there called GeoKey Manager who's doing this, but on the other point also have a nice feature of access control. So they can allow the access to keys for certain location while restricting access to other, to co-locations. But in any case, the problem is that conventional CDNs do not ensure forward security, and which means then once a location key leaks, that the customer keys are in danger. So what we did at Financial Crypto last year, we proposed a forward secure version for CDNs in general, and by also using an enhanced version of puncture encryption, where you now have something like called allow list, deny list encryption, where you can put something on an allow list, for example, the EU here, and you put something on the deny list, London, meaning that in Stockholm, the Stockholm keys can decrypt the ciphertext and get the customer keys on Rome, but in London this cannot be the case. The interesting point here is using puncture encryption directly adds forward security on top. And yeah, that essentially sums up this application. So the takeaways here for this talk are that through the example, we've seen a high demand in increasing resilience of the cryptographic keys in addition to the security and trust we need for cryptographic keys. Punctual encryption offers a simple solution on the cryptographic level, and particularly for the modern distributed and non-interactive scenarios. We've seen several applications, the zero RTT key exchange with forward security and replay protection, and forward secure content delivery network, beautiful works on searchable encryption and mobile cloud backup, Tor, and also updatable encryption are out there, and it seems it's gaining a little bit of momentum here. So with that, I want to thank you for listening. We have written a blog post about puncture encryption. Go ahead, and I invite you to use this link. And yeah, thank you for that, and see you next year, I guess.
All right, we're a little bit over, but if somebody has a question, I think we can do one. It's a race.
So thank you very much. I'm wondering what is the current state of scalability, because every time you puncture a key, it gets bigger and bigger.
Yes, that's not always the case. For example, using Bloom filter encryption, you just delete keys. So, but in the initial work or the work by Günther et al., you usually add the secret key state gets bigger, but if you're using Bloom filter encryption, it was incentivized. The puncturing is very easy there and very efficient. You just delete keys essentially.
Okay, so you can puncture with 1 million of messages?
Sorry, with what?
You can puncture 1 million of messages on a key?
It happens iteratively, but yes.
Thank you.
Okay, all right, let's thank the speaker again. Thanks again. And now I'm going to hand off to Peter.
All right. This is pretty much the end, so there's still a few things to say. So one thing is that Nigel just came running over to me and told me that I should definitely mention that you will all receive a survey. So in order to make RWC even better next year, we need your input. It would be great if you fill that in so that we know what to do differently, what to do better, and what maybe not to do anymore. Then, well, at the beginning, at the opening, we asked you to follow our recommendations for keeping the COVID cases small at the event. Thank you for all of you who did this. I can say so far we've received 2 reports of people who left early because they had positive COVID tests. I guess this is to be expected. It was an event with 500 people. But yeah, next days, when you return or when you stay, keep testing, be a bit careful. All right. Now for a lot of thank yous that I think is the job of the general chair to say at the end. First of all, I would like to keep thanking all of the sponsors of this event, and maybe you can start clapping while I'm clicking through here. This is going to continue for a while. So this event is really possible because of all of these sponsors. And if you're from industry and if you would like to see your logo in these final slides next year, please go and talk to Kenny, and he will get you set up, and you can, oh, we're just only at I, so this is alphabetically sorted, right? So I'll keep clicking here. All right, we're at Z now. Great. So now there's a few more thank yous that I would like to tell. First, I would like to thank Eric Riscola for sponsoring additional student stipends for this event. I would like to thank Bart and the Interfact Big Band for a great concert yesterday and for making sure that RWC got dancing cryptographers. Then I would like to really thank the RWC Steering Committee for really doing half of the work. This is very, very impressive, so thank you to the Steering Committee. And for the next one, I will need you to be pretty loud, because this is the team of the venue here. And okay, the AV people, they're in the back, but everybody else needs to hear you now. So they... So yeah, they did the other half of the work. You can see actually organizing this event is totally chill. Also because really all the people, all the students, the postdocs, the admin team from Radboud University and from MPISP, they did the remaining half of the work. And thank you very, very much to all of you. And those three halves are basically only for what you see here, but there's also, of course, the whole event happening online as a hybrid event in Zoom and in Zulip. And there's a huge thanks to Kevin and Kay for running this and for running night shifts here, because they're in the US. It's not exactly the most convenient time for them in Zoom and Zulip. So this is all from me, and now there's a few more thank yous I think that Helena wants to get rid of, so I'll hand over the ticket to her.
Okay, so of course we also had a program actually at the conference, and so there were speakers and papers submitted and all that, and so I would like to thank all of the members of the program committee that we had that helped put this beautiful program together. There were submitters to this conference, this symposium, and so everybody submitted. Not everybody got accepted, but all these people do a lot of work beforehand. And then we had external reviewers that helped us review all the submissions. At the event here itself, we had session chairs that helped us a lot get the whole thing going. Of course, we had all the speakers, contributed talk speakers, but also invited speakers. And then, hang on. Okay. Actually, we also had attendees. So thank you all for being here. And before we move to the really final information of the day, which Kazui is going to take over, I think we're missing one more person, and that might actually be Peter Schwabe, right here. Over to Kazui. You're on mute? You're mute. Wow. Okay.
And so now you hear me? And you see my slides?
Yes.
Okay. So next year, for the first time, RWC is coming to Asia, and it's going to be cherry blossom season in Tokyo. And the dates are March 27th to 29th. Well, what you can do in Tokyo, I'm sorry. It's going to be in the Bay Area of Tokyo. And you know, in Tokyo or in Japan, we have very good food. And you can try various ramen. And if you can buy some fake foods that you might have enjoyed in Tokyo. And the venue is called Plaza Heisei. In Tokyo, we have 2 airports, and Plaza Heisei is really in center of Tokyo. It's 15 minutes taxi ride from Tokyo Station. And this is how venue looks in night. There is a tram that walks around in this Bay Area, so you can take that also. And within a walking distance from the venue, you can see a gigantic Gundam, if you know what that is. And the venue is like this. We have one big room called main hall, and we have a medium-sized media hall. So I hope you can have lots of room and feel cozy and have a social distance between you between you people. And we have some breakout rooms upstairs. So I hope you can enjoy the conference comfortably. And that's all I have for today. My last message is to see you in Tokyo, in Japan, and save the date, March 27th to 29th, 2023. See you then.
Yeah, that's
I
it.
think we're done. Sorry, done.
Get home safely.